So welcome to Math 31. This is Lesson 8 on the substitution method. An important section because this is an important lesson because this is where we learn to basically undo the chain rule. And so it gives us more possibilities for integration, because up till now we can really only do it term by term, and we can integrate individual terms, but that's only really good for simple trig expressions and also sort of basic polynomial functions. So if you think back to the chain rule, for differentiation, dy dx is equal to dy du times du dx. Now we know that, and we're aware too, I hope, that that is how you differentiate composite functions, where you have one function nested inside another, usually in the form of a bracketed function raised to an exponent. Now this is another way to look at the same thing. The derivative of f at g at x is equal to the derivative of the outer f prime g at x times the derivative of the inner g prime at x. And so, given that that statement is true, then the reverse would also be true. So if we were going to take the antiderivative of f prime g at x times g prime at x, it will take us right back to the beginning. So this is leading somewhere. It's awkward the way it's expressed right now, but if we do make a substitution, so if we said, for example, let's make g at x equal to, well, just u, then this expression can simplify down to f prime at u, then g prime at x could be written as the derivative of the u function with respect to x, and then dx is still there. And then if you think of these as differentials, you can cancel the dx's out, and we would then get f prime at u times, or with the du there, not times, but that's just there as a basically window dressing. And what this tells us is that we can now, by using substitution, we can simplify or anti-differentiate complicated expressions. Or if you prefer, we can undo the chain rule. So the trick is, in the original integral, we replace one of the factors with a variable, usually u. Now it takes a bit of practice to get good at these, and that's because it's not the sort of thing you look at, particularly for the sort of mid-plus level ones. You don't tend to look at these and have an answer for it. So it takes a little bit of practice. But let's start with some fairly routine ones. So integrate the following. 2x times 3x squared minus 5 to the 7. Now this expression would be hard for us to do, or would have been hard previously, because we'd have to FOIL that out 7 times multiplied by 2x. So it definitely requires another method. And you will look at this and you maybe are even thinking that this, to get this answer, somebody might have differentiated by using the chain rule. So what we do, off to the side, we make a substitution for the 3x squared minus 5. So u is equal to 3x squared minus 5. And then when we differentiate that, so we go du dx. So even though ultimately we're trying to integrate, we have to do differentiation to get it set up. So the derivative of u with respect to x is equal to 6x. Now, you know that du dx doesn't mean du divided by x. It means the derivative of u with respect to x. However, if you did treat it like a differential, that is, like a variable expression, you could isolate the dx and express it as du over 6x. And the reason I did that is because I want to use substitution, the substitution I made, to express this one in a different form, where we can work it out. Because what we get now is the 2x is there, and that's the problem term. But this is 2x times u to the 7. And then dx we replace with du 6x over 6x. So see what we're doing. We're treating it like it's a quotient, like we're solving for dx as a variable in an expression. But what happens, which is what we want, is that the x's will now divide out. The 2 over 6 will also simplify to 1 over 3 u to the 7 du. So now we have an integral expressed in terms of u. That's what we want. Because now you don't have to take the 1/3 out, but I will just for the fun of it. So 1/3 times u to the 7 du. When we anti-differentiate, we'll get u to the 8, and a factor of 1 over 8. This is multiplied by 1/3, and then plus c. And then now, 1/3 times 1 over 8 is 1 over 24 times 3x squared minus 5. I don't know, that should be no x there, to the exponent of 8 plus c. Easy to check. If you were to differentiate that, it should take you to your answer. And the other thing is, this was an indefinite integral. That's why we ended up with a function for an answer. No substitution in yet. So that's how these things go. It takes a bit of practice to get good at the substitution. You're probably thinking already, well, the key is you take the bigger exponent, and when you differentiate that, it'll cancel out the smaller one. And that's generally true, but even more so, the substitution would be made with the part of the original integral that is the composite part. That is, has the exponent in brackets to the exponent of 7. So we'll see some more examples with that. As I said, though, it does require a bit of practice to get comfortable with these and to recognize when you do this and when you do not have to. Now, number 2, the composite part of the function and also the bigger exponent is this term right there. Because that's the one that's the problem, because it's to the exponent of 3. So off to the side, I do kind of the same thing that I've always been doing. U is equal to x squared minus 4x plus 5. So I'm not worried about the exponent, just the inner function itself. So du dx, is equal to 2x minus 4. Now the idea is that you cancel out that 2x minus 4. So when we isolate the dx, treating it as though it was a quotient, we get it in this form. Now you're probably thinking, are these ones all cooked up so they work out like this? The answer is generally yes, because if you think of that somebody had once upon a time differentiated an expression to get this, then they would have used the chain rule, which means that at some point they do have to differentiate the inner expression in order to make it work. So they do seem to work magically, but that's not as surprising as it may seem. So now we get u to the exponent of 3. I'll keep the 2x minus 4 there for now. Most of you will get very quick with the replacement, so you can go more directly to the answer. I replace the dx with du over 2x minus 4, and then we're in business. The 2x minus 4s go away on us, and then, which is, of course, what we want, and we end up with a very, very routine integral, u to the 3 du, expressed in terms of u. And then this becomes u to the 4 when we anti-differentiate, 1 over 4 u to the 4 plus c. And then that's going to be 1 over 4. Make the replacement back in for u, and x squared minus 4x plus 5 to the 4 plus c. That's how these go. Let's try a few more. This one's a little bit more complicated looking, and we haven't had to deal with the issue yet of which term do we make the substitution for, because most people take like the bigger exponent, but really the key is the exponent or the term or the cluster that is within a bracket, because that is in the chain rule setup or in the composite function, that is the inner function itself. So I'm going to do the same thing. U is equal to x squared plus 4. We do not need to go x squared plus 4 to the 1/2. That's just going to complicate things. So du dx, the derivative of u with respect to x is equal to 2x. So isolating the 2x, or the dx, excuse me, we get du over 2x. And then this is x over u to the 1/2 dx. Now, we do not want to write that on the denominator. So this is x times u to the negative 1/2. Bring it up. And then dx gets replaced with du over 2x. Now, this does cancel out our x's. I'm going to take that factor of 1/2 outside the integral. So 1/2 u to the negative 1/2 du. And now, if you deal with this one or anti-differentiate it, you'll get u to the add 1 on is to the 1/2. So you're dividing by 1/2, meaning you're multiplying by 2 over 1. I'll write that in. Most of you won't need that. 2 over 1 times 1/2 plus c. So those are going to go away, and we're going to get u to the 1/2 plus c, and then that's going to be square root. I'll put that in radical form. You don't need to do that. Of x squared plus 4 plus c. Now, if you have doubts about it, you simply differentiate the answer and then see if it takes you back where it is supposed to take you back to. Number 4. Now, some of these ones you probably would be happy doing them on your own and checking the answers afterwards, because this one is not going to produce much new. I'll still go through it though. 3x minus 1 is the bracketed expression, so that's going to be my u value. And you'll see right away that it also very neatly does a cancellation on us. Du dx is equal to 3. So dx is equal to du over 3. So this would simplify to 6 times u to the 3/2. Our dx gets replaced with du over 3. So this becomes the integral 2 u to the 3/2 du. So I'm going to bring the 2 out just because u to the 3/2 du. When you integrate, you'll get u to the add-on 1 would be 5 over 2. So that means you're dividing by 5 over 2, you're multiplying by 2 over 5, add on the c. So this gives us 4 over 5 times u, which is 3x minus 1 to the 5 over 2 plus c. And if you're inclined, you can check to see whether this one works out by differentiating. I won't bother though. Number 5 I'm going to skip over because it doesn't break any new ground. It's almost identical to number 3, I guess. Number 6, though, is where things do get, well, actually number 6 isn't that fascinating either. You've seen this sort of thing before, so I think what I'll do here is I'll just give the answer, and somebody let me know if there's any question with it. This should be negative 1 over 4 times the square root of 1 minus 4x squared plus c. So feel free to check that one out, but this too is like some of the earlier ones. And number 7, though, is noteworthy. Because up till now, when we make our substitution, you get a real clean cancellation of the unwanted extra variable. Now here you have to confront an issue, because we have always so far made the bigger exponent, the higher exponent, the substituted variable. So some of you are thinking, well, I should make u equal to x cubed, because that way when I differentiate it, I'll have an x squared, which will then cancel with what I want in my denominator. Unfortunately, it's not that simple. The bigger concern is to deal with the bracketed expression, the composite part of the function. So you do really have to make u equal to x squared plus 4. Now, had you made u equal to x cubed, it wouldn't have led anywhere, because in fact the square root of x squared plus 4, the square root of x squared is just x. It really isn't x squared after you take the root of it. So it wasn't. It looks like it's an x squared term, but it really isn't. So even if you'd wanted to, you couldn't have canceled it out that way. But we have to stick to the game plan, which is that the composite function has to be the substituted variable. But it is going to lead us to a problem, because when we go du dx, we get 2x. Now this is fine in the sense that the dx would then be du over 2x. But it's not fine in terms of our cancellation, because what we have is x cubed over top of, well, that's u, all right, to the 1/2. And then dx is going to be du over 2x. Now this gets rid of one of the x's, but not both. So now we have x squared. I'm going to take that u, bring her up, so u to the negative 1/2 du. But we're not really any better off. We still have to get rid of that x squared. So the way we have to do it is based on the original expression, or the substitution. If you go back into this, you'll see that we conveniently have u expressed in terms of x squared. So if you isolate the x squared, so express x squared in terms of u. So we would get u minus 4 is equal to x squared. And here we go. This we can handle, because we get u minus 4 multiplied by u to the negative 1/2 du. So it's all in terms of u. Now, what I would do to simplify this one, because some people will stare at it for a while and wonder what to do, the best idea, because it's a fairly simple binomial with a monomial outside of it, is just to distribute it in. So I'm going to multiply that u to the 1 in, and when I do that, u to the 1 times u to the negative 1/2 is u to the positive 1/2. And then minus 4 u to the negative 1/2 du. And I should actually have a bracket around that, just so it's clear what sort of integral we're up against. And then the rest of it should be fairly should work well. Except that I am forgetting that we do have a factor of 1/2 on the bottom. So let's take care of that. And then that would be 1/2. So that 2, that's from the original du over 2. So u to the 1/2 minus 4 u to the negative 1/2 du. Now you don't have to keep it outside the integral, but I like to do it so it's not in the way when we do integrate. So we get 1/2, and then keep it outside the big old bracket. Add on 1 to the u to the 1/2, becomes u to the 3/2. So with a factor of 2/3 in front. And then the second one, add on 1, and that takes you to u to the 1/2. So you're dividing by 1/2, multiplying by 2. I'm going to go directly to 4 times 2 is 8 u to the 1/2, and then plus c. Now you might want to distribute that one in, so you get 1/2 times 2/3 is actually 1/3. I'll put the u in right away. That's x squared plus 4 to the 3/2 minus 8 times u, which is x squared plus 4 to the 1/2, and then plus c. And we've done it. So those are more complicated. They do take practice, and that's really what it's about. You need to do enough of these so that you can recognize what you have to do with the substitution. Most people get quite good at the simple type of substitutions, but if it doesn't work, then this is what is necessary. And the best approach with it is that you just go in with a mindset, okay, I'm going to try a substitution. But then once you get to the point say right here, or right here, when you realize it's not going to cancel out, then you have to go into your bag of tricks to find a way to work it out. So you don't have to have, recognize at the beginning what it is that you're supposed to do. You just try a substitution, and if it doesn't succeed in eliminating the variable or all the unwanted x terms or whichever variable, then you try something else. So you can keep your mind fairly uncluttered. Number 8 is the same thing, and I would advise you to try this one on your own. I will put the answer for it, though, rather than take up a bunch of time. But first off, I'll even say that u is equal to x plus 5. So get you going on that. Du dx is equal to 1. So dx is equal to du. So when you break this one down, it won't get rid of it. The x term, because there's no x in the substitution for the dx, it won't eliminate. So the answer is 2/3 x plus 5 to the 3/2 minus 10 x plus 5 to the 1/2 plus c. And then I'm going to move on to number 9, and then I think I'll do number 10, and that will be it for this batch. I'll finish it off later. First time we've had to deal with trig, and here we have cos cubed x and sine x. Now this one will work out pretty nicely. The issue that most people have, they recognize that they're going to have to use a substitution because you've got two trig functions in there. But they don't really know what. And you also recognize that because the nature of the derivative of cos is sine, the derivative of sine is cos, give or take a negative, that they know that this is a chain rule problem. And you have to decide what the substitution is going to be. You could sometimes get away with two different substitutions, but I think that you would probably find, as always, the easiest approach is to deal with the composite function. This is the cos of x, which is a function, cubed. So to me, making u equal to cos x is the approach. With trig, as I said, you can sometimes make it work otherwise. But du dx, the derivative of cos x, is negative sine x. So the dx is equal to du divided by negative sine x. So this integral will now be expressed as u to the 3, and then we have sine x, which is unwanted, but the dx gets replaced with du over negative sine x. So problem has been solved. The sine x's are going to divide out, and we actually end up with negative u cubed du. So I will also take that negative outside just to get it out of the way. And when we integrate it, we'll get u to the 4, then 1 over 4 u to the 4 with a negative, plus c. And then this is negative 1 over 4 cos to the 4 x plus c. Let's do one more. T, sine t squared dt. It's a trig function. and there's a problem. This is not sine of t all squared. This is sine of t squared. So the argument is t squared. Now you got to decide what substitution you're going to use. Now you might have considered going u equal to sine t squared, because that's similar to the previous one. But what I'm going to do instead is let the u equal to t squared. So therefore du dt is equal to 2t. So therefore dt is equal to du over 2t. Now the issue of substitution for ones like these is not, there's no like perfect answer to it. What most people end up doing is, even if they don't have a clear idea at the beginning what they want to replace, they make a substitution, and if it doesn't work, if they can't eliminate the outside variable, then it is they have to try something else. So in here, if you take a look at the t squared, it probably makes sense to you that when you differentiate that, that's 2t, so it's going to cancel out your t. So, you know, a little bit of, you know, once you start the question at least, you can see, okay, this will work, this won't work. But it really does come down to practice to get, you know, total confidence in it. So we now have t times the sine of u, and then we replace dt with du over 2t. 2t, excuse me. And then, when this breaks, when we simplify the t's out, we get a factor of 1/2, which I'll take to the front. So 1/2 sine u du. So now, when we take the antiderivative of sine, we need to remember that the antiderivative of sine is not just cos, but it's negative cos. So we get negative 1/2 cos of u plus c. So this becomes negative 1/2 times the cosine of t squared plus c, and then we're done with it. So I'll stop there, and I'll finish the remaining ones off in the next class. But this is enough to get going on these and get a degree of confidence with sort of regular substitution problems. So thank you for your time.